Well, in problem number 2, we're given information in a data table about a pot of tea that's cooling. And the temperature is measured in degrees Celsius, the time is measured in minutes, and we're given data from 0 to 10 minutes. Now in part A, we're asked to approximate the rate at which the temperature of the tea is changing. Now rate to us means derivative, so we have to try to think of a way to find a derivative when given numbers in a data table. The way we're going to do that is we're going to go like this. We're going to think of h of b minus h of a over b minus a. That's how you find a derivative given numerical values. That's an average rate of change. Now, they want to know the rate of change when t is, 3.5. So we're going to have to approximate it looking at the data table. Well, we can see that 3.5 falls in between 2 and 5 on the time axis. So our a and b values are determined. We're going to go like this. We're going to go h of 5 minus h of 2 over 5 minus 2. That's going to give us 52 minus 60 over 5 minus 2. So let's see, that's going to be what? Negative 8 over 3. And the unit of measure will be degrees Celsius per minute. So we can conclude then that h prime of 3.5 is approximately negative 8/3 degrees Celsius per minute. If you made that a decimal, that would be approximately negative 2.667. Now in part B, they ask us to evaluate this integral, 1/10 times the integral of h of t with respect to t from 0 to 10. So first we should recognize that that's the average temperature. That's going to be the average value of the function h and the time from 0 to 10. And then they tell us to use the trapezoidal rule. And they tell us to use the trapezoidal rule, trapezoidal Riemann sum, with 4 intervals indicated by the table. So let's go to work. Our 4 time intervals are going to be from 0 to 2, from 2 to 5, from 5 to 9, and from 9 to 10. That's given to us in the table. And now, the area formula for a trapezoid is 1/2 times the sum of the bases times the height. Remember that the height of a trapezoid is the distance between the bases. In this case, the bases will be measured vertically, or the h of t values. So from 0 to 2, we're going to have 1/2 times 66 plus 60 times the height. From 0 to 2, the height is 2. Then from 2 to 5, we're going to have 1/2 times 60 plus 52 times the height, which from 2 to 5, that height will be 3. From 5 to 9, we'll have 1/2 times 52, bad looking 5, 50, that's not much better. There we go. 52 plus 44, and the height of a trapezoid on the interval from 5 to 9 will be 4. And then last but not least, from t equals 9 to t equals 10, we'll have 1/2 times 44 plus 43 times, that height is going to be 1. Okay, now using our calculators, we calculated this trapezoidal sum. And on our test, on the practice test, a lot of students stopped here, but we forgot one thing. What we just found was the integral from 0 to 10 of h of t dt. That's a trapezoidal approximation. So that's what 529.5 is. Now remember, the original problem, we're trying to find the average value on this interval. So we need to come in here now and multiply this integral by 1/10. So we have to multiply our trapezoidal sum by 1/10. And we're going to find that the average value of this temperature function, or the average temperature, from 0 to 10 is about see, divided by 10, that's going to be 52.95 degrees Celsius. Now, let's read the question, make sure we answered it. Using correct units, explain the meaning of this integral in the context of the problem. Yeah, well, there we go. We are done with this problem. The average temperature of the pot of tea is 52.95 degrees Celsius from time t equals 0 to time t equals 10. All right, let's go on to part C. Now in part C, here we go. In part C, we're supposed to evaluate this integral from 0 to 10 of h prime of t dt and explain what it means. So first of all, h prime is a rate of change of h. So if we integrate the rate of change of h, we'll get the total change. So now let's figure out how to integrate this. The integral of h prime is going to be h, and we're going to evaluate this from t equals 0 to t equals 10. So according to the fundamental theorem of calculus, version 1.0, it's going to be h of 10 minus h of 0. Let's see how we can work this now. If you look at the data table, we can tell that h of 0 is 66, and h of 10 is 43. So that's going to give us 43 minus 66, which is negative 23. So here's what we can say. We can say that integral from 0 to 10 of h prime of t dt is negative 23. Now what does that mean in the context of this problem? Well, h prime is a rate of change of the temperature. So the integral of h prime will be the total change of temperature. So we can say the t changed by negative 23 degrees, or the temperature decreased by 23 degrees. So let's say the temperature dropped, decreased a total of 23 degrees Celsius from t equals 0 to t equals 10. From t equals 0 minutes to t equals 10 minutes. And there we go. You could say the temperature changed, negative 23 degrees Celsius. That's okay. You want to be careful, though, because if you say the temperature decreased negative 23 degrees, that's a double negative, and what you're saying is not what you intended to say. Now we have to look at part D. Now in part D, we're given information about biscuits being taken out of an oven, because we all know that biscuits and tea go very well together. We have tea cooling in a pot and biscuits cooling that just came out of the oven. Let's go to work. The initial temperature of the biscuits coming out of the oven were 100 degrees Celsius. Wow, those are some hot biscuits. And the rate of change of the biscuit's temperature is given. So we're supposed to tell how much cooler the biscuits are than the tea. So what that means is we've got to do this. We've got to start with the biscuit's temperature, which is 100 degrees, and add the total change of the biscuit's temperature, which will be the integral from 0 to 10 of b prime of t dt. Now, this integral is going to give us something approximately 34.183. So it looks like the biscuit started at 100 degrees and then changed temperature in that 10-minute period, and they ended up at 34.183 degrees Celsius. So now here's what we're going to do. We have to find the temperature of the tea at 10 minutes, h of t, and subtract the temperature of the biscuits at time t equals 10 minutes. So let's see. H of 10, that's in our data table. H of 10 is 43 degrees, minus B of 10 is 34.183. So we can conclude then that the biscuits are about 8.817 degrees cooler. So we can conclude that the biscuits are about 8.817 degrees Celsius cooler than the tea at time t equals 10 minutes. Thanks for watching.